So finally, let's look at integration. So that's like the worst and most painful problem is integration. And the idea of integration is pretty straightforward. We're basically integrating the pressure times dA. Or you can say we're integrating the volume of the pressure distribution. So you can look at it both ways, but we're summing up all of those guys. So this is an example problem. It's actually in Hibbler, an example problem of a triangular shaped trough that's 1 meter high and 1 meter wide. If you look at the cross section of that triangle, this is 0.5 meters and this is 1 meter high. And so if you actually write the function of this line, y is equal to 2x. And so the slope of this line is 2, and x is your horizontal variable. And so when x is 0.5, then that gives us the height of 1 there. So that's our y function. We have to define a dA. So our dA is an arbitrary slice of this guy, and it's dy thick. The length of this guy is 2x. And so the dA is 2x times dy. Because I'm using a dy, I have to convert the x to y. And so if y is equal to 2x, then x is equal to y over 2. So I can plug the y over 2 in here into my dA. So that's the dA. The pressure is equal to gamma h. But h is the distance from the top of the tank down to dA. So the top of the tank is at 1 meter. The depth now, the height of this guy is y. And so my h is 1 minus y. Finally, my pressure is gamma times 1 minus y. So now we've defined pressure and we've defined dA. So my dV, or my dF that I'm summing, is pressure times dA. The pressure is gamma h times dA. The gamma h is gamma times 1 minus y. My dA is 2x, which is y over 2, dy. So just simplifying this, I've got a y here. So I've got a gamma times a y minus y squared dy. And if I integrate these guys from 0 to 1, and I plug in my gamma, this is fresh water, which is 9810. I get my force is 1.64 kilonewtons. And and that's the volume of that pressure distribution. So the pressure distribution on that triangular plate looks like this, but we've integrated him, and so the volume of that pressure distribution is 1.64 kilonewtons. If you wanted to find the location y bar, again, it's a centroid problem. And so now you're just going to take a y times this df and integrate those guys. So it's the same integral, but you're putting a y in there, and that's your numerator. And then you're dividing by the FR summation, which is this guy. And you take this numerator divided by the denominator, and you get y bar is 0.5, halfway up, which is kind of a surprise. And so that's a triangular plate where you're integrating for. And basically the procedure is the same for a circle, and these are on your, or for some other shapes. But there's really, again, no reason to do that when you can, if you look at this simple formula again, if you're looking at a triangular plate, our gamma z bar area formula is gamma, which is 62.4, the z bar, which is the distance down to the centroid of the triangle, and then the area, of course, is easy, 1/2 base times height. And you get the same r using our GZA formula without integrating. And so who in their right mind would integrate if you didn't have to? But if you're looking for a good time, set up the integral and do it. So, so those are basically kind of the principles of fluid pressure. You know, we looked at flat plate, constant width problems. We've looked at curved surfaces. We've looked at integration, the general case. And we've looked at the simple FR is equal to gamma Z bar area. And so these are principles that you can use for fluid pressure. Anyway, questions on that? And again, fluid pressure exerts a distributed load on a surface. And so it's a classic example of, in the real world, of distributed loads. Are these significant? Are these loads significant? I'll just share one more thing with you. Do you know what the specific weight of concrete is? So we said fresh water is 62.4. 62.4 pounds per cubic foot. That's gamma for fresh water. Do you know what a gamma for concrete is? It's about 150. So for concrete, gamma is about 150 pounds per cubic foot. And you probably can't fully appreciate that number. But if you're pouring concrete, if you're a civil engineer or you're a builder, and these are your forms, your concrete forms, and this is 10 foot high, which is not a super high wall, 10 foot, and you pour concrete into this guy, you basically have a triangular distribution comes down here. And so this pressure here is 10 times gamma at the bottom of your form, so the 10-foot wall. And you might think, well, that doesn't sound like very much. But you take 10 times 150, and you get 1,500 pounds per square foot. And so basically, if you got 10-foot tall forms and you poured concrete in there, for every square foot at the bottom of that wall, you basically have the concrete slurry is pushing outward here and is pushing outward here with a force that's equal to 1,500 pounds for every square foot. Those forms want to blow up. And so if you've ever poured concrete, you realize that these forms are very stiff and rigid, and there's lots of ties that basically tie the two halves of the forms together. And over a larger area, the number of ties that you have and the size of the ties have to create enough tensile force to keep those forms from blowing out from the pressure of the concrete that wants to push out the forms. And so it's not an insignificant problem for a civil engineer or for a contractor, especially if you're doing pour on high walls or high forms. It's a big issue. Fluid pressure can be significant in real life situations. So that concludes this lecture. Have a good day.